In these new weight loss medications, injections, Ozempic, Mounjaro, Wegovy, they are using a neurotransmitter as a hormone. I'm David Brown. I'm a bariatric surgeon. 98% of what I do is weight loss, metabolism, bariatric surgery, and I've been following this topic for quite a while with great interest. I think that there are things people need to understand, including physicians who prescribe these medications. I am very focused on human physiology in my practice, understanding how the human body really is supposed to work from a cellular, biochemical standpoint. And I think there are significant parts of this story that are being missed. And I think that people considering these injections need to understand them better. And I think that the physicians who prescribe these medications probably need to understand more about them as well. There's a great paradox in this story of these injections because the people who seem to respond to them most impressively, losing the most weight, are the people who don't have as much weight to lose. The people who are very overweight, super obese, don't usually have the same response to these medications. So what we see is the people who need weight loss the most don't respond quite as well as people who don't need it as much. And I would argue that the people who respond most impressively in weight loss to these medications are going to suffer the more severe side effects long term. So let me explain. We do have reports pretty widespread of some side effects people are noticing. One of them is a significant amount of muscle loss. In our clinic, we often see about 40 to 50% of the amount of weight that is lost is coming from muscle. Other clinics are reporting the same thing. And in your bigger studies, the published studies in JAMA and other medical journals, they show this also, that of the amount of weight lost on these medications, it's about 38 to 40% of the weight loss is coming from muscle. And if you know anything, if you study and follow longevity in the science, interested in longevity, you see this as a very big problem potentially. Another side effect that is being reported increasingly now is what we call gastroparesis. And this is, to some degree, paralysis of the stomach. People who are on these medications and stop taking these medications, some people are finding persistent nausea, vomiting, and inability to eat. And what they're finding is that this is because their stomach is paralyzed, essentially, that the motor nerves and the muscles that allow the stomach to contract, peristalse, and empty, those are paralyzed. These are some clues as to what is going on with these medications and why they are going to be problematic for some people. So what is going on here? Why do we see these side effects and how do these injections really work? The focus here is physiology and understanding how the medications are changing that physiology. That is the only way we can understand really obesity as well as some of these weight loss approaches. So these injections, they are synthetic forms of a naturally occurring peptide, a protein, a peptide made of amino acids occurring in the human body. It's called GLP-1, glucagon-like peptide 1. Now, this really is a neurotransmitter in a healthy human being. And with these injections, synthetic forms of this are being injected into a person's body in very high levels. And so really what's happening is a neurotransmitter is flooding the system and being used as a hormone. So to understand the way it's supposed to work, let's back up a little bit. Think of the brain as a computer, a supercomputer. It's more than that. But that is where the master controls are for most things, many things, including weight, appetite, metabolism, cravings, blood glucose, hunger pains, blood pressure, inflammation. That's where the controls are. Now, every computer requires input, the appropriate input to function properly. You think of sitting at a desktop, laptop, even a cell phone. you provide the input on the keyboard or the screen. Well, this computer, the human brain, also requires the appropriate input in order to function properly. And the way that it's supposed to be is that one of the primary, most important inputs into the brain comes from the gastrointestinal tract. Now, that GI tract, mouth to anus, is about 30 feet long. And in that 30 feet, there's over 400 square feet of surface area, which is like a small apartment. It's actually our biggest interface with the world around us, even though it's inside of us. Well, that 400 square feet of surface area is packed with specialized cells that are sensors, receptors. They are gathering information, collecting data, surveying. These are called enteroendocrine cells, and more recently they're called neuropod cells. And increasingly it's becoming recognized that they're a part of the nervous system. They're like a neuron or a brain cell. Now, on that surface of the cell, which is facing the inside of the intestines, that cell is detecting what's inside the intestines, sugar, fat, proteins, many different things. And on the other side of the cell, so we're talking a very small distance, on the other side of the cell, that enteroendocrine cell is releasing chemicals, molecules, neurotransmitters to signal across a very small distance to another cell. And that other cell is a nerve cell. It's a nerve ending. And these enteroendocrine cells, they release over 20 different molecules or neurotransmitters to traverse that tiny distance and signal to the nerve. And there are millions of nerve endings throughout the gastrointestinal tract. They coalesce into what's called the vagus nerve. Very important nerve. It is the primary connection between the brain and the gut. And so in this way, this huge surface area in the intestines is signaling to the brain, really using these neurotransmitters across this tiny little distance. Well, with his injections, they are taking one of those 20-some neurotransmitters, GLP-1, and they modify it so that it isn't broken down by the body like normally happens. And they're creating very high levels of this in the body. Now, it's important to note that in people who are obese, who have diabetes, when they're fasting, the levels of this GLP-1 in their blood are higher than normal. People who are lean don't have diabetes. They have higher fasting levels of that GLP-1. And again, in people who are obese, who have diabetes, when they eat a meal, the response to the meal in the level of GLP-1 is pretty wimpy. It's a small response compared to normal. Well, if you understand type 2 diabetes, we see the same thing with insulin in type 2 diabetics, that fasting levels of insulin in the blood are higher than normal. And their response to a meal, the insulin response is wimpy. It's a small bump. And so in diabetes, one of the fundamental problems, type 2 diabetes, is they have too much insulin. And modern medicine often will approach that problem by giving them more insulin. We do that. We say we, I don't. That is done because it lowers blood glucose, and we like that. We like to see that. We think that we're doing good, and it is good in part. But the bigger picture demonstrates something that's very problematic. In type 2 diabetes who are given insulin, their mortality rate, all-cause mortality, goes up pretty dramatically once they start taking what we call exogenous insulin shots, because fundamentally we're making the fundamental problem worse. And so what I would suggest is that in a significant number of people taking these weight loss injections, we're doing the same thing. We see a result that we like. People lose weight. Their diabetes gets a little better. But there's a picture that we're not looking at. And according to this other picture, in a lot of people, the fundamental problem is going to get worse with these weight loss injections. And that's why when people stop them, they gain weight, and their hemoglobin A1C, the other metabolic metrics worsen quite rapidly. Another important point is that in the gastrointestinal tract, again, this 400 square feet surface area, you have all these enteroendocrine cells releasing over 20 different molecules or neurotransmitters, peptides, to signal to all these nerve endings of the vagus nerve. It's an incredibly complicated system. When people do these injections, they have high levels of this GLP-1 or synthetic form of the GLP-1 in their blood. And instead of going through the normal physiologic route through the vagus nerve, it bypasses that vagus nerve, that connection between the brain and the gut. And this molecule in the blood crosses the blood-brain barrier, and there are GLP-1 receptors in the brain. In other words, some cells in the brain have the capacity to respond to this molecule or hormone in the blood. People assume that releasing GLP-1 in the gut, the way it's normally supposed to happen, and GLP-1 in high levels in the blood, crossing the blood-brain barrier and activating centers in the blood, that those two things are equivalent. It's the same thing. It's very much not the same thing. There's not a one-to-one relationship between GLP-1 receptors in the gut and those in the brain. And so although we see some results that we like and that are good, the assumption that we're using the normal system for good results, that's a big assumption, and I argue that's not true. In a normal person, of all the GLP-1 that's generated by the gut, most of it is, just about all of it is used to signal to the vagus nerve endings. And only 10% of that GLP-1 makes it out of the circulation of the blood beyond the liver. And that 10% really is broken down and deactivated within a minute. So what this tells you is that in nature, in a normal human being, this GLP-1, it's supposed to be working in the gut. It's not normally a hormone. And so increasing levels in people to a very high level, we're not reproducing normal physiology. We're perturbing the system in quite a dramatic way. To really understand the background in this, a bit on the nervous system. One part of the nervous system is called the autonomic nervous system. You can think of it as the automatic nervous system. This is the branch of the nervous system that really manages and controls most of what is involuntary, things you never think about. Dilation or constriction of the pupils, digestion, bladder control, all these things, pulse, breathing, blood pressure. There's a lot, and it would be far too much for us to control those things consciously. And so this autonomic nervous system really governs and takes care of that. Now, there are two branches of that autonomic nervous system, the sympathetic and the parasympathetic. The sympathetic, it's known as the fight or flight branch of the nervous system. You're in the woods, you're hiking, and you see a grizzly bear. You think of a shot of adrenaline, but there's a lot of things that happen in your body very quickly to help you deal with that scary situation. That is the sympathetic branch of the autonomic nervous system. It has a counterbalancing branch called the parasympathetic, and this is often known as the rest and digest branch of that autonomic nervous system. Digestion, healing, restoration, recovering. Ideally, in a person who's healthy, has a healthy metabolism, those two branches of the autonomic nervous system are in balance. Well, what we see in obesity, in diabetes, in heart disease, and in aging in general is a progressive shift of higher than normal sympathetic activity and lower than normal parasympathetic activity. And you see this everywhere. It affects every organ system in the body and every tissue. And this really is a reflection of health of the vagus nerve. The parasympathetic nerve really is sort of center control, along with the hypothalamus, for the parasympathetic branch of the autonomic nervous system. And fundamentally, driving obesity, diabetes, it could be argued that a fundamental driver is dysfunction of that vagus nerve, dysfunction of the parasympathetic nervous system. And you get this imbalance, too much sympathetic, not enough parasympathetic activity. And that system, the autonomic nervous system, it is a part of governing every tissue in the body, from cognition to digestion to the cardiovascular system, skeletal muscle. A lot of people don't know this, but that autonomic nervous system has a very important role in regulating and managing the muscles, skeletal muscles. And so when I hear that people are losing a significant amount of muscle on these injections, I back up. And why is this happening? It's happening because with these injections, this GLP-1 or the synthetic forms of it, they're bypassing the vagus nerve. They're not using the vagus nerve as is normal. They're bypassing it, crossing the blood-brain barrier and activating some places in the brain. But in doing that, they're bypassing the vagus nerve. And there's this important principle in nature, use it or lose it. You think of a muscle. If you don't use a muscle, it's going to get smaller. And fundamentally what's happening is by bypassing that vagus nerve with these injections, that nerve is not used as much and it becomes even more dysfunctional. So it increases dysfunction of the autonomic nervous system. And that is why people are losing muscle. That is why the stomach paralysis issue is raising its ugly head. And there's a lot of other things that we are seeing. So one measure of the autonomic nervous system and the balance in it is called HRV, heart rate variability. And it's fairly easy to measure and calculate. It can become very complicated. But in general, it is a measure of balance in that autonomic nervous system, specifically how well the parasympathetic nervous system is functioning. And what we see in people who are metabolically healthy, that when they use these injections, HRV goes down, meaning you have decreased function of the parasympathetic nervous system. There's higher than normal sympathetic activity at the site of nerves joining muscles. And so a good argument could be made that these injections in many people are accelerating the aging process. An important point is that if somebody already has a wrecked vagus nerve, they're diabetic, they're obese, they have high blood pressure, they have heart disease, they sort of have end-stage autonomic neuropathy, these injections are not going to do as much damage to those people. And it could be argued, it makes sense to use them in those folks. If someone is younger and they're not as metabolically ill, these injections are going to damage their vagus nerve because, again, it's bypassing the nerve. The nerve's not going to be used, and it's going to become more dysfunctional. So, in my opinion, it is a huge problem that the studies that have been done on these injections have been done on people with significant metabolic disease, initially in diabetes, heart disease. Most of the studies are done in people who have diabetes and heart disease. And so you can assume their vagus nerve is already fairly dysfunctional. And what was noted is that when on these injections, a lot of people seem to lose weight. It's a huge jump to take the injections from that group of people and use it in people who just want to lose weight, just need to lose weight. The assumption that it's doing the same thing or the side effect profile is going to be the same, that's a faulty assumption in my opinion. So the people that are the healthiest seem to be the ones that respond the best to these injections. It's because they don't have GLP-1 resistance. And it's in those people that their vagus nerve is going to be most impacted negatively. And they're going to suffer the worst side effects long term. This is that great paradox, or the unfortunate paradox. The people in whom these injections don't result in as much weight loss In part, it's because they do have GLP-1 resistance and their vagus nerve is already dysfunctional. So it's incredibly important for doctors who prescribe these medications to understand this physiology, and patients. I mean, quite frankly, people are ordering these things online and bypassing the medical community. You really have to understand what's happening long-term with these injections. I think that it's reasonable to think, and this is speculation, upon withdrawal of these injections, there's a chance there will be cognitive results, negative results, in other words, a decline in cognitive function. As well, if someone's been using these injections and they have a healthy metabolism and they're using them just to lose weight, if withdrawing those injections, reveals a more dysfunctional vagus nerve, I would expect that those people are going to be insulin resistant to some degree. They're going to struggle with high blood pressure, and they're going to be metabolically in a much worse place after using the injections than before. You might say, hey, you're a bariatric surgeon, you're biased in this. Yeah, everybody has bias. I'm biased, I'm sure. But I've been thinking about this for a long time, many years. And as a bariatric surgeon, I'm quite obsessed with understanding what causes obesity as well as why bariatric surgery works in the way that it does. We see much better results with bariatric surgery. And the reason for that is that bariatric surgery actually does the opposite. By stapling the stomach and the intestines, it's restoring the vagus nerve activity. So it is restoring normal physiology. Whereas these injections, they're bypassing it, sort of taking a shortcut. And I think in a lot of people, it's going to be an end negative for them. Hate to be a downer, but these are things that I don't hear anywhere, and I think it's very important in this craze of this social craze with these injections. Somebody's got to speak up and explain what the risks really are. Thanks for listening. If you're interested in more content, visit our YouTube page, Idaho BMI. I'm David Brown of Idaho BMI.